Okay, let's talk about these. So, what does it mean when they say, would you suppose, simplify the expression? What do they want you to do? What do you think? What's that mean? Ideas. Could mean multiply it out, but it doesn't. We're trying to write this in terms. This is similar to the stuff we talked about the other day, right? Where remember we had functions like the one that let's see. We had a function like this, right? We said if we have okay, what's the domain of that function? X not equal 0, right? Can't equal 0 because you can't divide by 0. Okay, so if I graph that, what's it look like? Remember?
It looks like a regular X line, except for there's a hole at 0.
Yeah, it does. Okay, how come? Well, if we simplify that and call it g of x, what can I do to that function to simplify it? I mean, it's pretty simple. What is x squared divided by x? X, yeah, I'm just canceling a factor, right, top and bottom. It's x. So this looks pretty simple, doesn't it, right? This is just a line. So if we graph the simplified version of the rational function, it looks really simple, right? Are they the same thing though?
No.
They're not. What's the difference? Yeah, there's a hole at 0, right? So you see what the strategy is here with stuff like this then. If we want to, so remember this is how we show a hole. We just put a little open circle there. So when we simplify, if we take an example like this one, this looks pretty complicated, right? In order to, for example, sketch a graph of this, it might be useful to cancel as many factors as we can and make this thing look simpler, right? But we got to be careful. When we simplify it, what do we have to also probably include then? Like for example here, it looked a lot simpler, but we still need to include the fact that x is not equal to 0, right? If we simplify the function, right? Because initially, the actual function has an x in the bottom. In its simplified form, that doesn't show up, but we still inherit the domain, right? Okay? So then what do you think we're going to do here to simplify this one? It looks pretty complicated now. Ideas, what do you think? Katie, any suggestions?
Can you cancel out the x?
So we can try to do some stuff, right? We can try to maybe cancel some things out. Good. On the top of the function, can I do anything to this first factor? Can I break that apart at all? Factor anything out? I can take an x, right? So this guy right here, I could factor out an x, and what am I left with? Okay. How about this guy right there? Can I do anything? Can I go any further with that? 1 plus x squared, does that factor? Ruby's shaking her head. No, she's correct. How come that doesn't factor? Is that a pattern? That's the sum of squares, and there's no pattern for that one, is there? Right. Kurt, how about this one? Can I go further with that one?
Difference of squares.
Difference of squares. Okay, so what's that one become then?
A minus.
Okay, a minus. So 1 minus x times 1 plus x. Good. All right. How about on the bottom? Anything I can do there? What do you think? Ruby, you see something there? What can I do? Go ahead, Sam.
Can you factor out an x squared?
Yeah, take out an x squared, right? So first step probably would be this one. Maybe we can do more with that one. So let's do this one separately, and then we'll plug it in. So that one's gonna become x squared times what's left over then? 1 minus x to the fourth. Okay, that's a little bit tricky. How are we gonna deal with that one? Luke, any ideas there how I can take a 1 minus x to the fourth? It's two terms, right? So if I'm gonna factor this, let's think back. This is good review. Think back to factoring stuff. Kristen, an idea?
You can do, x squared squared.
Okay, good. And let's, what Kristen's thinking here, tell me if I'm wrong. When there's two terms and we're factoring something, we're looking for a factoring pattern, right? I mean, we really only have 3 patterns. Sum of squares doesn't work. We've got difference of squares, and what are the other 2 we know? Sum of cubes and difference of cubes, right? So this part right here, we could make that into a difference of squares, couldn't we? It does fit. It doesn't fit a difference of cubes though. So we end up with x squared times something squared minus something squared. First something's a 1, second something's an x squared, right? Okay, and then what does that become? So difference of squares breaks up into what? So I got 1 plus, right? I've got like a squared where a is 1. And b squared where b is x squared, so I get 1 plus x squared and 1 minus x squared. And really, I guess, if we had been thinking ahead, if I'd been thinking ahead here, we could go, well, we'll just keep going with this. And then we'll look back and say, could we have maybe taken a little bit of a shortcut? Any of those factors break up any further? Okay, this one's another difference of squares, right? So we'd end up with an x squared times a 1 plus x squared. And then this guy's going to break apart into a 1 plus x and a 1 minus x, right? Okay, so now you work on that for a second. Go a little further with that. Okay, any ideas? Suggestions? What do you think? Gabe, any ideas? We could make that a little simpler?
Cancel with a 1 minus x, 1 plus x.
Sure, okay, let's cancel some stuff. So we can cancel, it looks like a lot of stuff, can't we? We can cancel the, oops, frozen. So we could cancel a 1 plus x, oops, there we go. 1 plus x, what else? 1 minus x.
X.
1 plus x squared, we could cancel those. And then look what we end up with. What is it?
End up with 1 over x.
Yeah, we just end up with 1 over x. Well, that's a lot simpler, isn't it? Right? But we do inherit all of the issues that we had with that original problem, right? So if we go back to the original expression, what's the domain? Somebody tell me one value that's excluded from the domain.
1.
1 is. Yeah, right there, 1 is excluded, isn't it? So we'd have to say, here's our answer, but x cannot equal 1. Give me another one, Jessica. What's another number that has to be excluded? That one said 1 can't be in the domain. What about that one? Negative 1. Ellie, give me another one. Is there going to be, well, what about this?
Split the whole.
What's going to be, say it again?
Let's split the whole and that's
Okay,
0.
it's, so which one is it?
Asymptote.
It's a whole.
Please excuse
Yeah.
this interruption.
Well, actually, hang on, no,
There
because
is
it,
a white
I see what
pickup
you're saying.
and a green pickup that is parked up by the P that need to be moved immediately. The construction trucks for the track cannot get through, so you need to move those immediately. A white pickup and a green pickup that are parked up by the P. Thank you.
I see what you're saying. You mean because there's an x over an x squared here and a 1 over x. Well, the final function looks like this. So which one is it then? It's an asymptote, isn't it? Right, because this is the shape of the final function. We just have to add a few holes here and there, don't we? So this factor on the bottom here is really, that's the same as that factor there, right? It's telling us the same thing, that x cannot equal 0, right? How about this one right there, that factor of the denominator? Does that one give us any exclusions to the domain? How come? Okay, yeah, because it doesn't have any real zeros, does it? Right? If I set that equal to 0, we end up with x squared equals -1, so we're going to get imaginary 0. So that one doesn't give us any equals, does it? Right? Okay? If we graphed this then, what's it going to look like? What's this complicated looking function going to look like? Let's just draw what it looks like first and we'll add the holes later. Maddie, what's 1 over x look like?
It's.
Somebody help me out here. Kipling, remember that? What's the 1 over x? That's one of our parent functions. What's that one look like?
I know some of the other ones.
Not that one. So, Kirk, help us out. What's that one look like?
It's the one where they have 2 asymptotes off of.
Okay, good. 2 asymptotes. So this is the one where we get a vertical asymptote goes through the origin and a horizontal asymptote that goes through the origin, right? And then it goes through the point 1, 1 normally, right? And then it goes through the point -1, -1 normally. But what do we have to do here? We've got all these exclusions. So at x equals 0, there's a hole. And, I mean, x equals 1, there's a hole. At x equals -1, there's a hole. Not 0. At 0, we've got that vertical asymptote, right? So maybe we need to take just a minute and do a quick review of something then. I'm just guessing that, so it's spring, so people are probably been here for certain things and not here for certain things, but let's just make sure we can do a problem like this. What if we had something like an 8.1 problem? Actually, it's 8.1. If I want to write that as a transformation of the inverse function 1 over x to graph it, what do I do? Divide, okay. Good, so how am I going to do that? What do you suggest?
2x plus 3.
Divided by x plus 1. We got 2 ways to do it. We could do long division. Could we use synthetic here? Yeah, we could. Let's go ahead and do synthetic then. So what number goes in the box? 1. What are my coefficients? 3. What goes here? You ever heard it? What goes there? What goes there? Okay. And so what's that tell me then? That tells me that this is equal to 2 plus the remainder of 5 over x minus 1, right? So normally we would have written it back in module 6 as 2 plus 5 over x minus 1. But if we write it as, yeah, did I mess that up?
No, I'm kind of confused.
Go ahead.
It's been a while.
Uh-huh.
I want to know, like, so did you get the 2 below the 3 if you multiply the 2 by 1?
By this 2 right here, yeah, whenever, remember, synthetic division, whenever a number appears below the bar, you multiply by the 0 that's in the box, and then whatever that product is goes there. And we just keep going across the line that way, and then you add, right? Add with synthetic division, opposite of what you do with long division, which of course is subtract, right? So that's how we would normally write this, but remember that what we're trying to do here, what we're trying to accomplish is we want to write this as a transformation of that parent graph, 1 over x. So we want to write it in the form a times 1 over x minus h plus k, right? And so we're going to put the 2 at the end because that's the constant, so that's k. we'll factor the 5 out in front of the fraction. So that's a, and we get 1 over x minus 1, right? Okay, so now, Maddie, what's that going to do? What are the values of a, h, and k again for this? A is, say it again?
It's 5.
5, good. What's h?
1,
1. K is
1, 2, or 2.
2. Yeah, okay, 2. So then, what's this sketch going to look like? Remember that h and k represent for our, where did I put that graph? Right there. H and k just represent the location of, it's not really a vertex this time, right? H and k is almost always, for any function you deal with, is going to represent the point that started off at the origin, right? So when it's been translated, h and k tells you where did it get slid to. It started at the origin, but what are its new coordinates? Well, this is an important feature here. Just quick review. This is the point where the asymptotes cross, and so that is the most important point in graphing that function. Even though it's not on the function, it tells us what the behavior is going to be, because all I've got to do is put a horizontal and a vertical asymptote through that, and they guide the sketch, right? So where does that point end up going here? Goes left one,
Right.
right one, because h is 1, right?
Yeah.
And
And then up 2.
up 2. Okay, so it's right there, right? So that's sort of the home point where the asymptotes cross. And then what does a tell us? I go normally I would go over 1 and up 1, but if this has been vertically stretched by 5, instead of going up 1, I'm going to go up 5. Yeah. So we go over 1, 1, 2, 3. So we go like up, clear up there. And so what that has the effect of doing is just pulling the curve further away from the asymptotes, right? And then I'd go back 1 and down 5. So right there. Whoops. Right there. Okay, right? Make sense? Okay. So, back to business then. Where were we? We were right there. So we've got this basic function here that looks like a 1 over x, but we just inherited some holes, right? But you get the idea then, when they say simplify, it really is useful to do, right? We can simplify this by canceling a bunch of factors, and it made it much easier to graph. I mean, initially that looks pretty darn complicated, right? But when all the dust settles and you cancel like factors, top and bottom, it's a pretty simple, in math we might call that an envelope of a function, because that's what it basically looks like, but we just got to go back and tweak it a little bit based on where the holes were, right? Okay, so how about that one? How could we write this rational function or expression equivalently? So we're going to write an equivalent expression. What's that mean? What's an equivalent expression? These words get thrown around a lot in math, but let's make sure we understand what the vocabulary means. What do you think? What's equivalent mean just in regular language? Equal. Okay, so if they're equivalent expressions, do they have to look identical? No, but they have to have the same value, right? Okay, so what could I do then if I want to make it have a denominator, x minus 5 over x plus 1? What is the denominator now if I factor it?
X minus 5.
5 over, what could I do on the bottom? What could I factor out on the bottom? Elizabeth, is there a common denominator or common factor there I could take out? 5. Leaving me with what? Okay, good. And I want the bottom, somehow I want this to, on the bottom, have the denominator x minus 5 times x plus 1. So how am I going to get from there to there? Duncan, what do you think? Any ideas? Mr. Devaney. Do I have a 5 in the bottom of this one? So what could I do right away probably? Yeah, I could cancel the 5s, couldn't I? Right? They're like factors. So I could do that, leave me a 1 on top. Now what though?
Factor it out.
Uh, So they are factored, but in its factored form, it doesn't say what I need on the top, right? We don't know yet. But I need to have an x minus 5 and an x plus 1 on the bottom. Well, how do I get an additional factor of x plus 1 on the bottom?
Times both by John.
Both. I gotta multiply by 1, right? I'm gonna multiply both the top and the bottom. That's it, isn't it? Right? Those are equivalent expressions then. How could you check that they're equivalent? Like, let's say you were doing this on an SAT test. How could you just check your work real quick and verify that this expression is equivalent, that this guy right here is equivalent to that guy? Say it again. You could set them equal to each other and solve, and you better get something like 5 equals 5 or 0 equals 0 or something, right? But there's maybe an easier way. Just a trick.
Plug something into X.
Yeah, plug something into X. Plug in a random X value, and if they're equivalent, what should they obviously do? Give you back the same value, yeah. Okay. All right, good. So then, here's the next step. So why do we do that? Well, we're working up to what we're really gonna I wanna look at today, sort of the main topic is, and that's kind of just warm up. I wanna look at how we do arithmetic with rational expressions. This is not, for you guys, this is something that you probably could do right now. I just wanna make it easier to do it. But you could, I think if you sat down, you could, on an SAT test, you could all power through these problems and probably get them right, but we just need to go through a few of the little intricacies. In order to add up or subtract rational expressions, and we're adding or subtracting anything that's rational, whether they're involved variables or not, it could just be regular old fractions. We know we have to get a common denominator, right? So let's focus on that for a second. Let's just look at that little subscale, right? It's a little bit more difficult when you don't have just numbers, if you have variables. So how am I gonna come up with a least common denominator for those two fractions, those two rational expressions? What do you think? How would you do it? Let's take numbers for a second. And I think this is a good strategy in algebra. When you want to remember, when you want to kind of piece together a process for doing something algebraic with variables, sometimes it's good just to start with numbers and kind of ask yourself, well, what do I do with numbers? And then I'll do the same thing with variables. It might end up looking a little more complicated, but the process is often exactly the same. So what if you wanted to add up something like, let's just say we want to add 2/3 plus 11/12. What would you do?
You multiply each by the 2/3 by 4.
Okay, and what's the thinking there?
Yes, and the denominator.
Okay, you want the denominator to be as small as possible, right? What if I broke these denominators into factors? What's the factor? What's the only factor at the bottom here, other than 1? We don't care about 1. 3. Okay, so that's 3. How about this one? If I break that into factors, it could be 3 times 4, which I could even further break up into 3 times 2 squared, right? And so then when I want to come up with the least common denominator, I just have to, really, if you think about this is a pretty easy example. We'll look at maybe one more difficult one with numbers. I have to come up with the smallest number that is going to utilize all of the factors, right, in each of the two denominators. So what if we did something like, instead of that, what if we did like, 5/12 plus 7/18? Okay, what are the factors of 12? 3 and 4, okay. So I could write that as 3 times 4. I could maybe even go 3 times 2 squared. What are the factors of 18?
3 times 6.
Okay, so this one's going to break up into 3 times 6
Or 9 times 2.
or 9 times 2. Either way you do it, if I say even 3 times 6, I can break the 6 apart further into what? If I want to break it into prime factors. 2 times 3, so I end up with 2 times 3 squared. Okay, so then what's going to be the least common denominator of 12 and 18?
6.
The least common denominator, you're thinking of Greatest common factor.
3?
Least common denominator is the same thing as the least common multiple, right? So what's the smallest number that both 12 and 18 will divide into?
3.
No, 3,
2?
no, it's gotta be bigger, right? Because we wanna know what's the smallest number they'll divide evenly into, right? Okay, it's 36, and you guys can just see that because you're good at math. But what's the process? How could you come up with that number 36 from those factors? What do you think? This one here, 12, is broken up into 3 times 2 times 2, right? Does that make sense? And so I have to have at least all of those, right? This one over here is broken up into 2 times 3 times 3, 2 times 3 squared. So I have to include at least all of those. But I don't have to take 12 times 18. That's a pretty big number, right? Because if I ended up multiplying both of those two numbers out, what would I end up with? I would end up with this times this, right? So I'd get 3 times 3 squared. Well, that's 3 to the 9th, or sorry, 3 cubed, not 3 to the 9th. 3 cubed times 2 squared times 2 to the 1 is 2 cubed. It's a pretty big number, right? That's 27 times 4, big number, right? Agreed? Like 108 or something, right? We don't need it to be that big. All I need to do is make sure that I'm getting that I'm getting at least those factors in there and at least those factors in there, right? So what's the smallest number of the prime factor 2 that I have to have? This one's only got a 2 to the 1, but that one's got a 2 squared. So I need a 2 squared, right? Because this one's got a 2 squared, so I'd have to multiply this function by 2 over 2. You see what I'm saying? This one, because I need if I were to only have a single 2 in the bottom, that's going to change this denominator. It's going to make it smaller, but I can't do that to the numerator because 5 is prime, right? So I'm going to distill this down to the prime factors of both denominators, and then I'm going to take the smallest grouping of those prime factors that's going to make sure that I'm covering both of the denominators, that I'm at least able to get both of the denominators out of that, right? So our denominator is going to be 2 squared times, what about the 3's? 3 is a common factor, but I only have a 3 to the 1 there and a 3 squared there. Well, I have to have at least a 3 squared because this denominator needs it, right? So I get 2 squared times 3 squared, which is 4 times 9, which is my 36. Yes, sir?
Where did the 3 cubed times 2 cubed?
That was just, I said if we were to take the product of all of those, we would have gotten 3 cubed times 2 cubed, but that's too big. We don't need that, right? Neither one of these individual denominators needs to have a 3 cubed, right? This one's got a 3 to the 1 and that one's got a 3 squared. Why do we need that extra 3? We don't, right? All we have to do to get to here, well, I need to get this denominator in the bottom of both fractions. This one starts off with a 3 to the 1 times a 2 squared, and I want to end up with a 2 squared times a 3 squared. So I'm going to multiply this fraction by 3 over 3 then, right? Because what does that give me? If I multiply by 3 over 3, then I get my 3 squared times 2 squared. You see? On this side, I need to end up with the smallest denominator I can build from all those factors of both fractions is my 2 squared times 3 squared. Well, this one's got a 3 squared, but it's only got a 2 to the 1, so I got to multiply this one by 2 over 2. Then I get my 2 squared times 3 squared. Right? You're just good at math, and so you don't consciously think about this, but in your brain, that is what you're doing, right? When you make that evaluation that 36 is the smallest number that both of those are going to divide into, maybe not in that much detail, but that's equivalent to saying what I just said here, right? Okay, let's try another one with numbers. And then so what would we get on top? if we add those up. 15 plus 14 is, what, 29? Right? Okay, try another one. Let's go. Let's take, okay, what are the prime factors of 10? 2 and 5, okay? So that's gonna split up into 2 times 5. What about the 15?
3 and 4.
Okay, so then what is the smallest grouping of factors that would include both a 2 to the 1 and a 5 to the 1, and a 3 to the 1 and a 5 to the 1? Well, and how come? Because whatever we get over here, the bottom has to have a 2 and a 5, right? And a 3 and a 5, so that's gonna just be a 2 times a 3 times a 5, right? Here's my 2 and my 5. It takes care of that denominator, right? And here is my 3 and my 5, which takes care of that one. The whole point being, I don't need to have the 5 in there again, right? The 5 is a shared factor of both denominators, right? So then in order to get 2 times 3 times 5, Drew, what do I have to multiply this one by? 2 times 3 times 5 in my denominator, because that's the least common multiple of both of these two numbers, right? Here I've only got a 2 times 5 now. Well, what do I need to multiply by to get 2 times 3 times 5? What am I missing?
Not sure.
3 over 3.
3 over 3. Well, see, I need to have that 3 to make it look like that, right? So I'm going to multiply by 3 over 3. Okay? How about over here? If I want to have the smallest product of the factors 2 and 3 and 5, I'm going to multiply that one by 2, right? But I got to do the same thing, top and bottom. So then what do I get on the bottom? 2 times 3 times 5 is 30. Here I get 27 plus 22, which is what, 41? Okay. One more. Let's see, I'm gonna get. Okay. Okay, to get a common denominator, right? What if I break the 20 down into its factors? What are the factors of 20?
5, 4,
Okay, and then the 4 really becomes,
2,
so the prime factors would be 2 squared times 5. And then here we're going to get, what?
3 or 15 times.
Okay, so if I break it into prime factors, so 3 times 10 would be 2 times 3 times 5. Okay, and if I write this, let's write this one this way. 2 times 2 times 5. Okay? So then my result over here, right, when I write this out as a common denominator, what do I have to have in the common denominator? What are my common factors? I've got 2's and 5's, right? What power of 2 am I going to have in here? What do you think? 2 squared or 2 cubed? Squared. How come?
That's like 2.
Yeah, because this one needs to have a 2 squared, right? And once again, I'm trying to find the smallest number that's going to include all of those factors and all of those factors. This one's only got a 2, but this one needs a 2 squared, right? Because 20 needs to divide into this number, right? So I know that I'm gonna end up with a 2 squared, right, which takes care of that. What about a 3? Well, this one's got a 3 in it. This one doesn't, but this one needs a 3. So I'm gonna multiply by a 3 to the 1, right? That takes care of that. And then they both have a 5 to the 1, so I could multiply by a 5. Okay, once again, if we look at this, do we include all of the factors of 20 need to be in there? Well, they are. There's my 2 squared and there's my 5, right? All of the factors of 30, whoops. I'll color code this here, there we go. All the factors of 30 need to be in there. Well, there's a 2, there's a 3, and there's a 5, right? So we're good. Okay, what's that work out to be? 4 times 3 times 5 is 60, right? And then to get that, I would have to multiply this one by 3 over 3, and this one by, what am I missing? I need to make it 2 squared. So 2 over 2, right? Okay? So what would that look like with not just numbers? If I break up this first, I want to find the least common denominator of these two fractions. If I factor top and bottom of this first fraction, what does it look like? Top I can't do anything with. I mean, you know, it's just -2 is -2. But the bottom, what can I factor at the bottom into?
3 times, in parentheses, x minus 5.
Okay, I can take out a 3 times x minus 5. What about over here?
4 times x plus 7.
Okay, the top is just a plain old 6x. I could take out a 4, and then I've got an x plus 7. So let's make a list then of all of the factors that are included in both of those, right? What's that list going to look like? I've got a 3, I've got a 4, I've got an x minus 5, and I've got an x plus 7, right? So the common denominator has to include all those, right? So what's that going to be? Well, none of those overlap, so it's just going to be 3 times 4 times x minus 5 times x plus 7. In order to get that denominator, what do I have to multiply this one by?
4 and x plus 7.
Yeah, I need a 4, right? Everybody see that? I need a 4 because that's not included, and I need an x plus 7, right? So we're going to get -2 times 4 times x plus 7 plus, what about this one? Well, I need a 3 and I need an x minus 5, right? Three, right? And then that would be it. On the bottom, I get the product of all those, which is 12 times x minus 5 times x plus 7, which I could multiply out. And on the top, I get, well, we'll pick this up. You get the idea? Okay, we'll keep going with this.
Sorry. What's the placement test?
We won't do it until June. Yeah. What's that?
Are you going to the middle school meet?
When is it?
I don't know. I didn't sign up, but I'm going obviously because my mom's gonna coach. Like, the coach.
Oh,
I don't really know what like. Are we getting excused early or something?
oh my gosh, I don't know. I'll probably go help out with it.